Now in the previous videos, we have talked about the ideal op amp, right? We have said that these three characteristics are present in an op amp, in an ideal op amp, and we use that. And if we have an op amp circuit like this and we just give the two voltages, the output is either going to be the positive power supply or the negative power supply, and this circuit behaves like a comparator. So it's either saturated on the positive side or on the negative side, other than one case where these two inputs are same. But let's say we could build an op amp circuit where V naught is not infinity or it's not saturated. Okay, so V naught is finite. Let's say we could build a circuit. What would that mean? What would that mean with these assumptions? Just look at this first assumption. So V naught is equal to AD times VD, and we are saying that this V naught is going to be finite. However, we have already assumed that this AD is infinite, right? So if V naught has a finite value, what does that mean for VD? It means that VD will be equal to V naught by AD, and therefore as AD tends to infinity, this is going to tend to 0. So if the output is finite, we can assume that the inputs at the two input terminals, the non-inverting and the inverting terminals, are the same. Okay, and which another way of saying it is that VD will be 0. Okay, so that is one implication that we use as we build our circuits. If we want a finite voltage here. So let me just take an example and show you what I mean. Okay, so here's a circuit that I have built, and in this circuit, let's start by just assuming, of course I know that this is true, but let's just start by assuming that the output here is finite. Okay, now if the output is finite, according to our assumption 1 or characteristic 1 of this ideal op amp, we know that the voltage at this point, which is V in plus, should be the same as the voltage at V in minus. Now what is the voltage at this point at the non-inverting terminal? You can see that the non-inverting terminal is connected to ground, and ground is usually taken as 0 volts, and so this is 0 volts, 0 volts. And if the voltage at the non-inverting terminal is 0, what would be the voltage at the inverting terminal? Now again, because we assume that the voltages of this at both the inputs are the same, so the voltage at this point is also going to be 0. Okay, now we know the voltage at this point, which is 0, which means this is the same point, so the voltage at this point is 0. So we could write the equations for the current through R1, and we could write the equations for the current through R2, right? What is it going to be? So the current through R1, IR1, is going to be what? IR1 is equal to, what's the voltage across this resistance? So there is a V in here and there is a 0 here. So the voltage across is V in minus 0. And if you divide that voltage by the resistance, you should get this current. So we can write IR1 equal to V in minus 0 divided by R1. Now what is IR2 similarly? Now the voltage across this resistance, and which is the current IR2, is, so the voltage across this resistor is going to be 0 on this side and VO on the other side. So the current is going to be 0 minus VO divided by R2. Now notice that I'm taking, now because the current is flowing in this direction, I'm taking this side to be the positive side. And therefore I write 0 minus VO, not VO minus 0. So the current IR2 is going to be 0 minus VO over R2. Okay, so all this by just applying the first condition or the first characteristic of our op-amp model. Now let's just bring in the second characteristic of our op-amp model. Now what is the relationship between the current that is flowing through R1 and the current that is flowing through R2? Now we know that the current that flows here is divided into two parts, right? It's divided into this current and this current. Remember the Kirchhoff's current law? Now this current of course is IR2 and this current is IR1. What is this current? This current we have already called I in minus. And what is the value for this current? It's equal to 0. Look at the second condition. And therefore we can say IR1 equal to IR2 because all the current that flows through this resistance flows through R2 as well. There is no other way for the current to go, right? So now we have an expression for IR1, we have an expression for IR2, and we have this equation. Let's just replace equations 1 and 2 in 3, and what do we get? What we get is V in minus 0 over R1 equal to 0 minus VO over R2, which implies V in over R1 equal to minus VO over R2. So what is the output voltage? The output voltage is minus V in R2 over R1. And now you can see that we started off by saying we are going to assume our output voltage to be finite. And you can see that if the input is finite, if our input is finite here, and if R1 is not equal to 0, then the output is finite. And therefore, we have our starting assumption is met. And what is the output going to be in terms of the input? It's going to be minus R2 over R1. So applying these two characteristics of the ideal op-amp, we have found out the output of this circuit. We have not yet applied the third characteristic of the op-amp, right? What does this tell us? What this tells us is that this output would remain this no matter what circuit is connected at the output. So you connect whatever you want to connect here, the output is always going to we will be able to maintain this output at the output of this circuit, right? So you cannot load the op-amp. So we've just calculated the output of this circuit, and the output is given by this equation here. And you can see that, okay, what kind of mathematical operation is this circuit doing? You can see it takes the input and it multiplies it by a factor of R2 over R1, and it gives you a negative sign along with it. So this kind of a circuit is basically multiplying a constant, right? And we call this multiplication with a constant value amplification in electronic terms. So this circuit is an amplifier. Okay, but while amplifying, it also gives us this negative sign at the beginning, and therefore we call this circuit an inverting amplifier because it inverts the input and amplifies it. Now the amplifier will have different gains depending on what R2 over R1 is, and R2 over R1 could be greater than 1, or it could be less than 1, or of course it can be equal to 1 as well. But there is always going to be a negative sign associated with it. So the gain of the amplifier is written as VO over Vin, and that is minus R2 over R1. Okay, and because the gain is negative, we call this the inverting amplifier. So that gives us one more block in our block of in our set of electronic blocks to be used for designing different circuits. So we now have a circuit that can actually uh, do amplification. Now we were able, with voltage dividers, as we saw before, we were able to get gains of less than 1, right? You were able to get gains of less than 1 when you just put two resistors in series and took the output from the middle of it. But you were not able to get a gain of greater than 1, which the inverting amplifier allows you to do.